So let's get started. Section 1 on page 1 of your notes, Introduction to Phases of Matter, talks about the basics, solids, liquids, and gases. But let's take a deep dive into what makes them unique on a molecular level.
Okay, let's unpack this. So solid phase, section 2, still on page 1. We're talking about those tightly packed particles. They vibrate but don't move around much.
Exactly. Think of a rock. It stays a rock. Doesn't matter if you put it in a box or on a table. It holds its shape.
It's like a packed subway car at rush hour. Everyone's shoulder to shoulder, kind of jiggling, but not going anywhere.
Perfect analogy. And that's why solids have a definite shape and volume. Now let's move on to liquid phase. Section 3, page 1. Here, those particles are a bit more relaxed.
Yeah, they can move around and slide past each other, right?
Right, like people mingling at a party. They take the shape of their container, but the volume stays the same.
So like water in a glass. It takes the shape of the glass, but you still have the same amount of water. Okay, now things get really interesting. Section 4 on page 1, gaseous phase. Those particles are like, well, imagine kids let loose on a playground. They're running everywhere, filling up all the space.
They've got tons of energy and no fixed shape or volume. Think of blowing up a balloon.
Oh, yeah.
The air inside, it's a mix of gases, and it expands to fill the whole balloon. Now, there's a special case mentioned in section 4.1, still on page 1, vapors.
A vapor is what, like a gas?
It is a gas. It's the gaseous state of a substance that's usually a liquid or a solid at room temperature.
Like steam from a boiling pot. It's water, but it's a gas.
Exactly. Or think about dry ice. It's carbon dioxide, but in its vapor form.
Huh? Bet you didn't know that.
Okay, let's flip to page 2. Section 5 dives into temperature and pressure, really important concepts, especially when we're talking about gases. Section 5.1 defines temperature. It's the average kinetic energy of those tiny particles, how much they're moving around, basically.
Higher temperature, more energy.
You got it. More jiggling and moving around.
Like a dance party. Those particles are getting down.
Yeah.
Now, what about pressure in section 5.2?
Pressure is all about force. It's the force those little particles exert when they collide, like a billion tiny ping pong balls bouncing off the walls of a container. You feel a tire, it's firm because of the air pressure inside.
Right. And our notes mention standard atmosphere pressure in section 5.2. What's that all about?
Right. It's the pressure at sea level, an important reference point, like a baseline measurement.
Okay, so then section 5.3 on page 2, standard temperature and pressure, or STP, like a universal measuring stick.
Exactly. Scientists needed a standard set of conditions to compare different gases, and that's where STP comes in. Standard temperature and pressure, it's 0 degrees Celsius and 1 atmosphere of pressure, a handy reference point.
Got it. Now, section 5.4, temperature-pressure relationship in a closed system. This is on page 2 still. It says when you heat a gas in a sealed container, the pressure increases.
Think of it like this. You have those gas particles, and they're like tiny bumper cars.
I like this analogy.
As you heat things up, they start zipping around faster.
More collisions.
Exactly. More collisions, higher pressure. Makes sense, right?
Totally. So now let's move on to page 3, kinetic molecular theory of gases, or KMT. What's the big deal about KMT? Section 6.
Okay, so KMT, it's a model, helps us visualize how gases behave at the molecular level, like a set of rules those gas particles try to follow.
Rules. But are these rules always followed perfectly? Do real gases always play by the book?
That's a great question. Section 6.1, ideal versus real gases, addresses that. Ideal gases, they're like the perfect students, always following the rules of KMT, no volume themselves, and they don't interact with each other.
Right. But real gases? They don't always behave so perfectly, do they?
Nope. Real gases do have some volume, even if it's tiny. And they can experience weak, attractive forces between them. Like in a crowded room, people can't help but bump into each other.
So under what conditions do real gases behave more like? Ideally.
According to section 6.1, high temperatures and low pressures, like giving those particles plenty of space to roam free.
Freedom for the gas particles. So it's all about creating that ideal environment where they can act like independent particles, right?
Precisely. The more they act individually, the closer they get to that ideal behavior.
Okay, I'm starting to see how this all comes together. Now we're getting into some formulas. Section 7 on page 4. The combined gas law. A bit intimidating at first glance, isn't it?
It might look complex, but trust me, it's a powerful tool. It connects pressure, volume, and temperature. Tells us how they all change in relation to each other.
Bevioro. Bevidi.
Okay, so if I'm compressing a gas and the temperature stays the same, I can use this equation to figure out how much the pressure will increase.
Exactly. It's all about those relationships.
Pretty handy. So in section 7.1, still on page 4, combine gas law in a closed system, we're back to that temperature-pressure relationship.
Remember when we talked about heating up a sealed container? The pressure goes up as the temperature rises?
Yes.
Well, this section shows us why that happens mathematically. The pressure is directly proportional to the temperature if the volume is constant. So if you double the temperature, you double the pressure.
It all ties together. Now, what about section 7.2, Avogadro's law, still on page 4? What's special about this one?
Avogadro's law, it's all about the amount of gas and its volume. Equal volumes of gases, same temperature and pressure, will always have the same number of particles. Doesn't matter what type of gas. So two balloons, same size, temperature, pressure, one filled with helium, the other with oxygen. Same number of particles inside?
Exactly. And a key thing to remember from Avogadro's law, it's highlighted in your notes. 1 mole of any ideal gas takes up 22.4 liters at STP.
22.4 liters, got it. Okay, moving on to section 8, vapor pressure on page 5. Vapor pressure always seemed a bit mysterious to me. Can you shed some light on it?
Okay, imagine a closed container. You've got some liquid at the bottom.
Okay, I'm picturing it.
Some of those liquid molecules at the surface, they have enough energy to escape. They become vapor. And those escaping molecules, they create pressure above the liquid. That's vapor pressure.
So those energetic molecules are pushing against the air above the liquid.
Exactly. Now, section 8.1, factors affecting vapor pressure on page 5, tells us two main things impact vapor pressure: temperature and intermolecular forces.
So if you heat up a liquid, more molecules escape, higher vapor pressure.
Exactly. You're giving them more energy to break free and become vapor.
What about those intermolecular forces? How do they affect vapor pressure?
Well, those are the attractions between molecules. They can make them stick together or let them go free. Weaker intermolecular forces, those molecules escape more easily, leading to higher vapor pressure.
Got it. So a substance with strong intermolecular forces, like water, will have lower vapor pressure than, say, rubbing alcohol.
You got it. And there's example 8.1. Interpreting vapor pressure data on page 5 uses ethanol. It asks, at what temperature does ethanol have a vapor pressure equal to standard atmospheric pressure?
And we can find that in Table H on page 3, those reference tables, right?
Right. Table H tells us ethanol reaches a vapor pressure of 101.3 kilopascals, which is standard atmospheric pressure, at about 78 degrees Celsius. That's its boiling point.
Makes sense. So now we're on page 6, section 9. Behavior of gases. A good overview of how temperature and pressure affect gases.
Yes. Section 9.1, effective temperature and pressure, reminds us that when you increase temperature, gas particles get more energy, which means higher pressure if the volume stays the same. And decreasing pressure gives them more space to spread out, and they act more ideally.
It's all about that balance. Give those gas particles space to do their thing, but not let them get too cozy.
Exactly. Now, section 9.2, conditions for ideal gas behavior on page 6. It's all about those specific conditions again.
High temperatures and low pressure.
Right. Create that perfect environment for those gas particles to behave as independently as possible.
Okay, so we've covered all the main points.